For the past 2 years, we have been investigating and proving an original concept for a new weapon system, which uses the ocean for its base, its concealment, and its protection. We've named the concept ORCA. As conceived by us, ORCA is an encapsulated missile system, simple and reliable, relatively inexpensive, and highly invulnerable. It's designed for deployment in a dormant state for long periods without maintenance on the ocean floor, to be called up and launched by coded sonar commands. We've subjected to analysis and feasibility tests the key principles and some system hardware. We have no doubt that ORCA is technically feasible, and our analysis of its cost effectiveness shows it to be superior to any other existing or presently planned weapon system. ORCA appears ideal for deployment in waters adjacent to selected European countries. In this application, it might serve to implement the statement made by the President at Ottawa, in which he said, "We look to the possibility of eventually establishing a NATO seaborne missile force." ORCA's development background will be traced by the Technical Director of Astronautics, Charlie Bossert.
ORCA evolved from studies we started in 1957 to explore missile weapon system requirements of the future. We were especially interested in increasing missile survival without compromising effectiveness. The investigation pointed to a need for a ballistic missile with a high accuracy and strike power, but with a much lower purchase and operating cost than systems then in procurement. From our studies, conducted in 2 phases and financed with corporate funds, came a concept for a ballistic missile which seemed to have remarkable advantages over existing weapons. In phase 1, we determined that a small light ICBM was feasible, and we designed a mobile highway launcher for such a weapon. But further analysis of the truck scheme revealed a number of problems, including high operating costs and manpower requirements and hazards involved in highway operation. During the second phase, we investigated 30 operational schemes covering land, sea, and airborne deployment, and considered such factors as cost, invulnerability, logistics, and date of availability. Among the plans considered were highway-based moving strike forces, tractor crawler systems deployed in wasteland areas and moving in random fashion between dispersed revetments, ground basing in which live and decoy missiles could be periodically alternated between capsules, airborne missiles deployed aboard existing aircraft, and missiles mounted in external paths aboard standard nuclear and diesel submarines. But the most promising concept, offering the highest effectiveness at the lowest cost, proved to be ORCA, an encapsulated missile system that rests on the ocean floor until commanded to surface and launch itself against pre-selected targets. The ORCA development came under direction of Kerry Coughlin, the project engineer.
The ORCA concept is simple. A missile is stored in a sealed capsule and deployed on the ocean floor. The weapon is designed for hands-off maintenance and inspection policy and remains dormant for long periods, except for a sonar receiver running on low-drain batteries. In other words, it does not wear itself out with unnecessary activity, but keeps an ear open for trouble. It's actuated by a time-frequency signal, which can be coded securely. When activated, the ORCA discharges its ballast, achieves positive buoyancy, and the entire container heads to the surface. As the capsule emerges from the water, its cover is jettisoned, and the missile is launched to its selected target. One of our first development steps for ORCA was to test the feasibility of the launch sequence and the stability of the overall design. This we did at sea 2 years ago. Lead engineer on these tests was John Transu.
For the tests of the Sea ORCA, we selected this site in Mosquito Cove, off San Clemente Island in the Pacific. The missiles and capsule used in this test series were quarter-scale models of an ICBM ORCA system. Although these models did not include all of the subsystems that would be used in the operational system, they presented a hydrodynamically and dynamically true representation of the ORCA launch system. The ORCA will be taken to the deployment area by a ship. The buoyancy chamber will be flooded, allowing the ORCA to descend. It will be lowered on a cable almost to the bottom. Then the exact coordinates of the location will be inserted into the missile guidance computer through an umbilical. The ORCA will then be placed on the bottom, and the cable and umbilical will be detached and retrieved. The ORCA system will reside dormant and unmanned on the ocean bottom in waters bounding the European continent. The period of dormancy will initially be 1 year. Depth of deployment areas varies from 300 to 2,000 feet. Even at the greatest depth, the capsule and shock isolation system can absorb a 1,000 psi overpressure from a nuclear explosion. A low-drain sonar listening device, which operates continuously, will be the only non-dormant element in the encapsulated system. Warm-up and gyrocompassing are accomplished on the ocean floor. After the launch heading has been determined, the launch sequence will be initiated. The ballast water in the buoyancy chamber is evacuated pneumatically, after which the ORCA is buoyant and rises to the surface. It breaks the surface at a velocity of 60 feet per second. When the capsule emerges from the water, the forward closure is pyrotechnically jettisoned. The missile fires and flies from the capsule. The test series confirmed analyses showing that the missile will egress without collision with the capsule.
Mr. Rosenbaum has told why we are developing the ORCA system, and Mr. Blostert has explained how he arrived at the concept. Now, I would like to show you ORCA's superiority to other systems planned or in being, as well as selected deployment areas in Europe. Cost-effectiveness studies of this system were based on credible threats against different strategic weapon systems. Against the Minuteman, an enemy could effectively use missiles and aircraft to bombard the positions which are known. Against Polaris, an enemy might employ killer submarines and ASW forces for trailing and destruction. These threats are not likely to be effective in a simultaneous attack because of the operating area available to the sub. If the enemy elects to effect attrition on a limited warfare basis, he risks the danger of this limited action escalating into an all-out war. Against a truck mobile system, an enemy could use agents to monitor and report on force movements and direct missile fire at the commencement of hostilities. Submarines could be used against the ORCA, but they would be operating with active sonar in dangerous waters controlled by our forces. An enemy might also elect to establish positions of the ORCAs and defer destruction until a simultaneous attack is launched. But ORCA redeployment during the recycle period would prevent the enemy from pinpointing more than a small fraction of the force at any time. For the cost-effectiveness comparison, no R&D costs are shown for Minuteman or Polaris, since these systems have been developed. All cost figures are in millions of dollars. The initial investment and 5-year operating costs are shown on a per-deployed missile basis. Here is the total budget required to deploy 300 ORCAs and maintain them for 5 years. The same budget would provide for these force sizes. Here we have the number of missiles surviving an attack which would come in a different form for each strategic system. In the case of each strategic system, the economic worth to the enemy is equal to the cost of 268 ICBMs. This attack consists of 268 ICBMs for both Minuteman and the truck mobile system, and each missile has a yield of 10 megatons and a CEP of 1/2 of a nautical mile. Submarines and ASW forces are employed against Polaris, and the size of the anti-submarine force is equal to the ICBM budget. However, the probability of kill on Polaris is so low that for our comparison, all missiles survive the initial attack. The ORCA is attacked by missiles after submarines have located a portion of the force. So in ORCA's case, the budget provides for a composite force of submarines and ICBMs. Of the four systems, only Polaris and ORCA show a high degree of invulnerability. And in the case of Polaris, this survival comes at an extremely high cost. In the ORCA system, we have a ballistic missile capable of operating to ICBM ranges. This depicts a 47,000-pound missile in a capsule 108 feet long. In air, the total system weighs 350,000 pounds. It can deliver a 200 KT warhead 5,500 nautical miles, with an additional 180 pounds allocated for penetration aids. At lesser ranges, ORCA can deliver warheads of greater yield or multiple warheads. Of the deployment areas we investigated, the most promising appear to be the Aegean Sea, where approximately 1,360 units could be stationed, including 143 near Athens. The southwest coast of Norway, between 5850 north and 6035 north, for 150 units. In the Mediterranean Sea, with 92 units along Spain's south coast from Adra to Cartagena, 112 units from Cartagena to Cape San Antonio, and 543 units from Barcelona to Rome, including the island of Corsica. The English Channel and the southern coasts of Ireland and England for a possible 4,000 units. Early in the ORCA studies, we recognized that one of the keys to its successful development was the problem of command and control. We're solving that problem, and our results to date will be explained by Pat O'Leary, the assistant project engineer.
We have investigated many methods for communicating with the ORCA system. Of these, sonar techniques show the greatest promise. Analysis to date has convinced us of its technical feasibility, but experimental data is both meager and inconclusive.
Therefore, in order to verify our analysis and to obtain the needed proof, we modified a vessel for sea trials of a prototype sonar command system. Our purpose is to explore the problems associated with transmitting secure, reliable, binary digital coded messages through the sea. Though much data is available on sonar, this information concerns itself with the detection and listening problem for the most part, with only a small part directly applicable to our requirements. Our ultimate objective for this test series is to produce a secure, reliable command signal over a minimum distance of 5 miles. The prototype command system included a hydrophone and decoder, which we lowered to various depths to test message reception. To produce the signal, we use a transmitter and encoder, driven by a power amplifier that provides up to 1,000 watts of radiated power. We are running repeated tests to gain conclusive data on transmission quality and power requirements, and to determine the effects that distance, temperature layers, and bottom conditions have on the signal. At this filming, we have transmitted command quality sonar signals over 3 miles at a depth of 500 feet. We will continue this phase of the test series until we achieve our objective of transmitting a minimum of 5 miles at depths below 300 feet and for various bottom conditions. In the second phase of this test series, we intend to activate a prototype ORCA capsule with sonar commands that bring it to the surface. To surface when commanded, ORCA will require a simple, reliable method of ejecting water ballast to obtain sufficient buoyant lift. We have designed and tested a technique which meets these requirements. Water ballast is contained in baffle chambers, then forced out through a discharge pipe by high-pressure air. We employ 3 baffles, each with discharge holes spaced at 120-degree offsets. This approach allows at least 50% of the water to be discharged regardless of the roll orientation assumed by the capsule on the ocean floor, and with up to 20-degree off-horizontal capsule attitude. As the capsule begins to rise, its center of gravity, center of buoyancy relation causes it to rotate to vertical, thus allowing further discharge of the entrapped water. In this manner, at least 90% of the water will be ejected under all probable deployment conditions. In order to evaluate our buoyancy and command control techniques under realistic conditions, we designed a 1/4 scale prototype of the ORCA capsule for use in sea trials. Now nearing completion, the capsule contains sonar receiving equipment and the ballast exchange system. In the near future, we will begin tests with the combined system by calling the capsule up from the ocean floor with sonar commands.
You have seen in capsulized form what we have done so far with this new weapon system. We've satisfied ourselves that it is completely practical, and we recommend, therefore, that the development, production, and deployment phases of the ORCA concept be implemented.